You may have already heard of topology optimization, or heard about how it can lead to original structure designs. But have you ever heard of topology optimization in electromagnetism? If you want to learn about it, especially for electromagnetic applications like electric motors, that's what this video is for. Let's take a closer look. Topology optimization was first developed in mechanics. For a given structure, it helps remove all unnecessary material while making the structure more rigid. Here, topology optimization produces an original chair structure that is as rigid as it is light. In this case, and most other cases, topology optimization tends to create shapes that are often not intuitive and beyond state-of-the-art. For example, the chair we show here is so elegant that it's not for daily use. It's called the bone chair, and it's considered a work of art. It's part of the permanent collection of major museums, and it was designed by a topology optimization software developed by Opal R&D activities. In engineering, topology optimization is about designing serious things. It's used to design bridges, motorcycles, buildings, and also cars. But first, what is it? How does it work, and how could it lead to new non-intuitive designs? And the big question, how can we use it in electromagnetism? Let's talk about a concrete application like an electric motor design problem. It will be a perfect illustration of topology optimization in electromagnetism. There are many types of electric motors, but let's take a look at a particular one, the permanent magnet synchronous machine. It is widely used in the automotive industry. A PM synchronous machine is composed of two parts, the stator and the rotor. The stator is made up of a ferromagnetic structure and coils. Three-phase alternating current is supplied to the three coils with a phase shift of 120 degrees. This phase shift causes the created magnetic field to rotate. Let's call this magnetic field BS. As for the rotor, it is made of a ferromagnetic structure and magnets. Those magnets generate a static magnetic field that we can call BR. When the stator field BS interacts with the rotor field BR, it causes the rotor to rotate. And in this way, electric power is transformed into movement of the rotor. Now, let's talk more about the design problems of that motor. Here, one of the most common problems is the magnetic field generated by the stator BS. Along the red line, the radial component of BS must be as perfect as the sinusoidal curve, but in reality it is not, and this causes a famous problem commonly referred to as torque ripple. Torque ripple means simply that the rotor movement is not as smooth as desired, and to remedy this, engineers should make BS as close as possible to a sine. One solution is to design a toothed rotor, but what does that design look like? It is often seen as an optimization problem. Don't worry, we'll keep it simple. The idea is to simply minimize the difference between the desired magnetic field and the real one by making a couple of modifications to the shape of the teeth. But the big question is how those shape modifications can be described mathematically. The first and most straightforward option is to describe the shape by a set of parameters. Here we describe the shape by four parameters, A1, A2, A3, and A4. The idea is then to modify these parameters in order to decrease the difference d. This is called parametric optimization. Okay, that's nice and simple, but is it enough? The answer is no. Indeed, as we can see here, parametric optimization gives results that have the same initial shape. In other words, the solutions that we are looking for will always have the same shape. This means that in the domain of all possible designs, we are searching for solutions in a very limited space. This small space could be called the explorable space. This means that if the solution must come out of that explorable space, there is no chance to find it. So, to explore more space, new types of design modifications should be made possible. And that's what shape optimization is made for. In shape optimization, the shape is described differently. Instead of defining the four parameters, we define a displacement vector v. V indicates at each point of the shape boundary how much and in what direction the deformation of the shape should be carried out. The idea then is to choose V in order to minimize the difference D. Doing so, this time, we could find shapes different from the initial one, which means that we have a larger explorable space than is available with parametric optimization. That's nice, but is it big enough to contain all the possible solutions? The answer is again, no. To clarify this point, so far our methods have only been able to modify the boundary of the shape. They have not been able to create holes inside that shape, which means that the final designs have exactly the same number of holes that the initial shape has. In other words, the final solution doesn't change its topology, because changing topology is, by definition, the capacity to create or eliminate holes in a given structural design. And that's what topology optimization is all about, allowing us to create holes. So, how does it work? Generally, there are 4 types of topology optimization. Here, we are going to talk more about the density method in a very basic way. The idea consists of first meshing the parts to be designed. Then we decide for each mesh either to keep the ferromagnetic material or to replace it with an air or vacuum mesh. That decision is based on crucial information that is computed using a mathematics concept called the adjoint variable method. The adjoint variable method is a concept that is beyond the scope of this discussion, though we may address it in another video. All we can say is that the adjoint variable method provides a crucial piece of information known as sensitivity, and that makes it possible to solve such a huge problem in a more efficient way using a classical gradient-based algorithm. Here is how it works concretely. At each iteration, the adjoint method quantifies mesh by mesh the relevance of replacing ferromagnetic material by air, or the inverse. In doing so, you can see the holes gradually appearing in the structure. Here we can see that deciding mesh by mesh is a key idea behind discovering new topologies and shapes, and this without any a priori information. This is why the optimization of topology makes it possible to explore a larger space than shape or parametric design, resulting in designs that go beyond the state-of-the-art. That's it. We hope we have helped you to gain a better understanding of these concepts. Thanks for watching. If you would like to know more about us or to discover more electric motor design problems, please feel free to contact me. In the next video, we will see how TO is used in a real electromagnetic application. We're going to talk about the design of Hall effect thrusters, an electric propulsion technology to make satellites move in space. Stay tuned.